Hi everyone, I'm Lisa Lippincott, and I am here to talk about value in a procedural world. But first, a little note. It is a long story. It's a story of a sort I think most of you are familiar with. Many of you have participated in a story like this. It's about how way back at the beginning of a project, you make a decision, or maybe you don't even make a decision. You take a step in a certain direction, and whatever you did, it's good enough. The project works, it becomes popular, other people start to use it, other people start to join in to advance your project. It becomes a big thing that many people are using, that many people are helping with. And as something becomes a big thing like that, it gains a kind of social momentum. Things that you did back at the beginning become really hard to change because you'd have to get all of these people to change them at once. And sometimes you find yourself thinking back to the very beginning of the project, or maybe you're explaining it to somebody new involved in the project, and you look at what happened way back at the beginning and you think, that doesn't make a lot of sense. That's hard to explain. That I can't really tell people why that happened. But you're not going to change it. It's way too much trouble to change, and it seems to work. So this is one of those stories. And this particular story involves the way we say things like, 5 is bigger than 2, which is the sort of thing you might say if you are concerned with values, numbers, and their sizes. And I want to point out that when we say 5 is bigger than 2, just grammatically, these two words, 5 and 2, function as names. They are single word determiner phrases that purport to refer to an individual thing. And the question is, what do these words refer to? What are 5 and 2? And how would we know that 5 is bigger than 2? One person with an opinion on this subject was the Greek philosopher Plato. Plato believed in a world of ideals. And I want to be clear, he believed in ideals the way he believed in rocks. These are real things, just in some faraway place. And in Plato's view, 5 being bigger than 2 is just a fact about that faraway place. It is a fact like the idea of house. The existence of the idea of house was a fact in this faraway place. Lollipop tree, if Plato had known what a lollipop tree was, he would say that the ideal of a lollipop tree is in this faraway place. It's just a thing there. So Plato believed that values are things, and I want to emphasize this, things that are real like rocks are real. You might ask, if you think of 5 and 2 as things in a faraway place, how do we know that 5 is bigger than 2? Do we know somebody who's been there and come back and brought pictures or at least a story about that place? And I don't know anybody personally who claims to, but Plato said, yes, I do. In fact, Plato would say that back before we were born, back before we were even conceived, all of us lived in this platonic world before we existed in the human world. And when we lived in that world, we could observe that 5 was bigger than 2. And perhaps with a little prompting, we could remember that 5 is bigger than 2 now that they're far away. I've got to say, this seems like a bizarre idea to me, that we were transubstantiated from some distant world. But it at least gave some explanation of what we're talking about when we talk about values. And this idea that values are things, that values are real as rocks, or perhaps even more real than rocks in a kind of Nine Princes in Amber way, has come to be known as Platonism. Skipping forward a little in the story, one famous Platonist was Gottlob Frege. Gottlob Frege, big proponent of Platonism. I don't know if he believed in the before you were born part of it. But one person who thought numbers, values, were things that are real like rocks are real was Gottlob Frege. And he did an interesting thing. He introduced these 2 symbols that are in the middle of the slide, for all and there exists, into mathematics. Today we don't use those symbols. We use these symbols instead. And this was in his work, The Begriffsschrift. I won't read out the entire title. And this is the point where Platonism became part of mathematics. This is mathematics getting a notation that is about whether things exist or do not exist in the Platonic world. And this greatly broadened the scope of mathematics. Before we could talk about, 2 plus 2 being 4, but we couldn't say 2 is a thing that exists in a mathematical formula. But since then, Platonism has, it took a while to catch on, but Platonism became a real part of mathematics. We can do proofs about it. Frege went on to come up with some rules in his Grundlagen and Grundgesetze about what things exist in the Platonic mathematical universe. And he had this idea that we would use those to prove other things exist, prove lots of things about mathematics. But what happens? Along comes Bertrand Russell and finds a contradiction in Frege's rules. They cannot possibly work. But I should say, this thumb down that I have given to Bertrand Russell is a great misstatement of his opinion. He was a big fan of Frege's work. He just felt the details should be right, and clearly they weren't. So Frege attempted to revise his work. It didn't work out. But someone else working about the same time was Georg Cantor. And Georg Cantor proposed the idea that the things that exist in the Platonic mathematical world, the values, are sets. All of them are sets. We don't need anything but sets. What's in the sets? Other sets are in the sets. So in Cantor's view, When we talk about 5, we're talking about a set. We're, in fact, talking about the set depicted on the slide here. That's 5. Cantor also came up with a list of rules that explains what sets exist, how you construct one set from another, and what happens. Along comes Bertrand Russell and finds a contradiction in it. Again, it's a promising start, but you need to get the details right. So, moving along, not too much later, Ernst Zermelo takes a stab at it. He designs a theory we call Zermelo Set Theory, specially designed to get that annoying Bertrand Russell off his back. What happens? Along comes Abraham Frankl. Frankl convinces Zermelo that his theory isn't expansive enough. It doesn't have enough sets. So the two of them together put together Zermelo-Frankl set theory. With more axioms, you can show more sets exist. Later on, Zermelo decides that ZF is still insufficient. It's missing something that he calls the axiom of choice. And so he extends ZF to make ZFC, Zermelo-Frankl set theory with choice. So today, ZFC, Zermelo-Frankl set theory with choice, is the foundation of essentially all modern mathematics. This is our standard model. And if you're talking to a mathematician, if you're talking about values, you are talking in the context of ZFC or something very close to ZFC, except for some very fringe stuff. And I want to emphasize that ZFC is a theory about what exists in the Platonic mathematical world. It is fundamentally based on this idea that there is this other world where sets exist and that they are real like rocks are real. So ZFC is fundamentally an extension of Platonism. Fortunately, for those of us that find the whole remembering things before we were born a little weirdly mystical, there are other ways to look at it that still let you talk to mathematicians. One of those, one that I dabbled with in my youth, is formalism. Formalism is the idea that when I say 5 is bigger than 2, I am just saying 5 is bigger than 2. I am making some mouth noises, but I don't mean anything by it. This is just a step in a long chain of reasoning I might go through that starts with something in the real world and maybe ends in something in the real world, but the things I say in between are just incantations without any particular meaning. In my later years, I have come to understand the vital importance of being earnest. Formalism is anything but earnest. Formalism is sticking a winky face at the end of everything you say so that you can't be held to believe in anything. Not a big fan of formalism these days. Something that is, I think, a better explanation of what a mathematical thing is a philosophy known as fictionalism. Fictionalism is the idea that when I hold up my fingers like this and say 5, I am invoking a metaphor. I'm saying fingers are like a thing called 5, and that is very much like holding my fingers up like this and saying Spock. I am constructing a metaphor that relates my fingers to a work of fiction. And that's a really neat thing about metaphor. Metaphor lets us connect the real world to not just other parts of the real world, but also to stories. And stories are very convenient because many people can be equally a witness to a fictional story. So if you make a good story that has a good metaphor in it, you can pass that around and relate the real world to it. And I like fictionalism because it at least explains that back and forth between Zermelo and Frankl, adding to their theory, revising it. This wasn't, in my mind, them racking their brains to remember things before they were born. It wasn't them receiving further divine revelation in the way Cantor, as I understood it, understood his axioms to be divinely revealed. But instead, it's the two of them collaborating on a story. I don't know if they actually thought of it that way, but I can see it as them collaborating on a story, one with deliberate intent. They wanted it to be rich in a certain sort of metaphor to explain certain sorts of things. A parable, if you will. You can think of them as writing the parable of the sets. And now other people can read the parable of the sets and relate things in the world to that story. But I don't want to suggest that everything is rosy with fictionalism. There are some issues. One of the issues that comes up very quickly is the question of which Spock. There are several different Spocks from several different Star Trek universes. And we know that these are different Spocks because there's crossover fiction where they meet each other. So when I talk about Spock, I have to worry about which Spock I'm talking about. And the same is true of 5. There are multiple, for a fictionalist, there are multiple fictional mathematical universes. And they each have their own 5. And yes, set theorists write crossover fiction where these universes interact. Another problem that you have to think about to truly embrace fictionalism is maybe a little deeper, and it's, why do we expect a mathematical proof to carry more weight than saying it worked that way on Star Trek? So fictionalism also has its problems. And I bring this up not to give a full overview of all theories of value. There are others. But I just want to point out that there are different ideas of fundamentally what a value is. Is it a real thing, like a rock? Is it just an artifact of how we interpret mouth noises? Is it a thing in a work of fiction that we believe in the way we believe in things we don't believe in? And I'm going to take a step back and point out that to one degree or another, all of these theories are kinds of essentialism. They are fundamentally about the question, what is a value? Essentialism is hard. If you're asking, what is a thing? What is its essence? What is it at its heart? It's hard to answer that question without getting inside and finding out. If you're on the outside, it's hard to get to that, to deep into that question. So I'm going to turn my attention to an easier sort of philosophy, which is functionalism. Functionalism asks the question, what does it do? What is the function of this thing? How does it interact with the outside world? And in my mind, functionalism is easier because I am usually in the outside world for these things, and I can observe how it affects my life. If you're asking the functionalist question, you can perform experiments and see what happens. And that's where I'm going to turn here. I'm going to restrict my view to procedural programming and look at how we perceive value in procedural programmings and what we can say about how values behave in procedural programs. So I'm going to treat value as if it were a natural phenomenon and try to examine what it does. So the first question that we run into is, how do we observe value? And here I have one thing to say, which is, in a program, distinct execution paths reflect distinct values. That is, if we see a piece of code and we note that sometimes it executes a certain statement and sometimes it does not execute that statement, we can attribute that to an idea of value. We say the value of B was different at this branch, and so the program did a different thing. And execution paths in programs are very often observable to us. I want to point out that what we're seeing here is not at all an individual value. What we are seeing is distinction in value. So in some sense, what is real here is maybe not the values themselves, but the distinctions between them. I know that's a weird thing to grasp. There is a particular branch of mathematics called pointless topology that follows exactly this rule, that it looks at distinctions independent of what is being distinguished. So if you want to go down this road mathematically, I think pointless topology is a helpful field for you. So if we have these different possibilities, we can consider them as part of a whole, an ensemble. That's the mathematical word for this, a collection of possibilities where we can draw distinctions. We can say turning left at this branch is meaningfully different from turning right. So an ensemble with a topology on it lets us describe the possibilities here. And that's how we observe, as far as I can tell, the notion of value in procedural programming. But there's a little bit more to it. Talk's not over yet. The next question is, what do we observe values doing? That is, are there rules that we observe values following? And there are some. If we see a piece of code like this, where we have this B and we branch on it twice, we observe that there are only two sorts of executions of this code, not four. Both branches are going to turn the same direction. So there is something that causes both branches to turn the same directions. What principle explains that? And I'm going to call that principle stability. We have this idea that the value of B was set and it remained stable through both of these branches. And because these branches were based on value of B and the value of B was stable, they will go in the same direction. So there's our first principle, stability. Sometimes objects are stable. When they're stable, they have a stable value. The situations under which values are stable are more complicated. That's a whole nother talk. This isn't all. There are other principles. If we look at a slightly more complicated piece of code, here I am making a copy of B and then branching on the copy. And what happens? Once again, both branches will go the same direction. There are only two possibilities, not four. But stability can't connect these two branches because the value of C didn't even exist when the first branch happened. There must be some other principle that connects these branches that lets us know that these two branches will go in the same direction. And this is the principle I call substitutability. This is the property of a copy. A copy will drive branches in the same direction as the original. So here, stability and substitutability combine to link these two branches together. Is there another? Yes, there's another. Here is another piece of code. Once again, in this piece of code, we observe that the two branches always go the same direction. There are two possibilities, not four. And in this piece of code, there is no substitutability connecting them. There's no copy being made. Instead, what's happened is I've repeated an expression. I have repeated A greater than 2. And we have this idea that when we repeat a call to greater than, that we at least sometimes expect to get the same result. That is, repeating a function call repeats the output of the function call, or at least repeats the important parts of the output of the function call, what I'm going to call the discernible output, the output that we see as mattering. So repeating a function call repeats the output. How do we know when we have repeated a function call? When we call the same function and repeat the input. So it's not true that greater than always produces the same discernible output. it produces the same discernible output when we feed it the same discernible input. This is a topological property called continuity. That is distinct outputs, that is meaningfully distinct outputs, come from meaningfully distinct inputs. If we step back a little further, we have to wonder, well, how do we know that the discernible inputs to greater than were the same? And this breaks down into two pieces. The first part of the input, A, we understand is the same because of stability. A is stable, it fed the same discernible input into both calls. The other one, we're not seeing stability there. What we're seeing is the discernible output of an operation we call to, which initializes an integer. So to, like greater than, when fed the same input produces the same output. But there is only one sort of input for to. It draws no distinctions. You might use it to initialize an object over here or a different object over there. It doesn't distinguish. It always produces the same value. So this is the picture of how those two branches are connected in this bit of code. And that's our third principle, repeatability of function calls. Distinct outputs come from distinct inputs. And so far as I am aware, those three principles, stability, substitutability, and repeatability, cover all we observe about how values behave. I know you were probably taught at some point in your life about the distributive law or something. The distributive law is just a big pile of stability, substitutability, and repeatability. So these are the basics. And they affect the way we program. If we want to describe what the interface to a function is, we need to describe how it affects stability, substitutability, and repeatability. That is, for stability, we need to describe how whether certain periods of stability end or begin at a function call. That's a job for the function interface. For substitutability, when we have a function that produces substitutability, that makes a copy or observes that something is like a copy, we need the interface to talk about substitutability. And for repeatability, we need function interfaces to make clear what the function sees as meaningful distinctions in input and what it sees as meaningful distinctions in output, so that we can apply the rule of repeatability that meaningful distinctions in output come from meaningful distinctions in input. So let's take a look at this in a function interface. And here is my favorite notation for a function interface. It's actually a block of code that's divided into two parts by this word implementation. And the part above the implementation line is executed before the implementation is executed. The part after is executed after the implementation. And this is the code that we can use to check that the caller and the function are behaving according to an agreed upon set of rules. And the caller is responsible for the portion above the implementation line, the called function is responsible for the portion below the implementation line. So in a function interface, and here I've picked a particular function that I'm sure you've all used at least once, which is assignment of a double to a double. A built-in function, it's very simple to understand to the extent that floating point is simple to understand. But I think you all know what's supposed to happen in this function. So what happens in terms of stability? Here, the caller has to give up the stability of the left-hand operand in order to do an assignment. Before the assignment, the caller knew that left-hand operand was stable. It held a consistent value over time. But at the point of assignment, the caller gives up that stability. After the assignment, the caller receives new stability. The state may have changed. There was a gap. It's a different stability that the caller receives. So the value of left is stable before the assignment, and it's stable after the assignment, but it's not stable across the assignment. Substitutability also comes into play here because we are making a copy, but it actually comes into play twice. We're making two copies when we assign a double to a double. We are making a copy of the address of the double because assignment has a result. The result of the assignment is a reference to the left-hand operand. So a pointer to the left-hand operand is substitutable for a pointer to the result. Those two are aliased. Substitutability also comes into play more directly, perhaps. The value of the result is substitutable for the value of the right-hand operand. So two substitutabilities in an assignment operator. And finally, a little redundantly, that we can ask, what does it mean to repeat an assignment? And by my reading at least, to repeat an assignment, you have to repeat the right-hand operand. And what does repeating an assignment guarantee? It guarantees that the result, which is alias to the left-hand operand, will be repeated. If I do two assignments with the same right-hand operand, they will result, the left-hand operands will be the same afterwards. So that's stability, substitutability, repeatability used in an assignment. I think those principles cover everything that goes on in an assignment of a double to a double. But to truly understand this, to get it down to terms where we are on very solid footing, where we can explain it to a computer perhaps, we have to know what it means for two values to be meaningfully distinct, what it means for them to be not meaningfully distinguished. We need something in our programs that goes with this interface that explains what a distinction between doubles is, or a distinction between pointers in the case of the aliasing. You might think that equality, the double equal operator, is tailored perfectly to this thing. After all, equality really is about seeing what things are the same and what things are different. But it doesn't work. For stability and repeatability, we are talking about two things that exist at different times. You can't explain stability using double equal because you can't compare this now to this in the past. Repeatability, it works the same way. It is difficult to compare the thing that is happening now to something in the past that you may no longer have recorded. So you can't use the double equal operator as a basis for what is stable or what is repeatable. There are also some problems with substitutability. And these are more technical problems, but in C++, equal can be true for pointers of different provenance, even if those pointers aren't substitutable for each other. One might be one past the end of an array, and the other one might be a different object that landed near the array. Equal also will return true for floating point zeros, even though one is positive 0 and one is negative 0. And there's a reverse problem in floating point that if you make a copy of a nan, of a not a number value, it won't compare equal to the original. In fact, a nan won't compare equal to itself even if it's the same object. And those are substitutable. It's making a copy is the fundamental thing that gives us substitutability. So equal and substitutable are similar notions, but they're not quite the same. So if we turn back to our interface, none of this can be handled, can be based on the double equal operator. That is, stability can't be based on it because stability is about two different times. Repeatability can't be based on it because repeatability is about two different times. And both of these substitutabilities can't be based on it because one is about aliasing, where it matters that the pointers are not merely equal, but actually have the same provenance. And the other is about floating point numbers. And we know equal and substitutability don't match up for floating point numbers. So none of this can be explained in terms of equal. You need a different idea of what values are indistinct and what values are distinct. So how can we construct a formal language for describing what values we will consider alike, what values we will consider not clearly distinguished from each other, and which ones we will consider clearly distinguished from each other? We can fall back on distinct execution paths reflect distinct values. We will use execution paths to show distinctions in value. So if I show you a piece of code like this, an if statement, I am showing you that I care about dividing the possibilities of the world into two camps. One where the if statement turns left, and one where the if statement turns right. And I'm going to call that a meaningful distinction in value. And I'm going, in order to be precise, I'm going to say meaningful, for a meaningful distinction, you have to make a difference in what statements are executed. I'm not interested in anything below the statement level. That's more of an engineering decision. I tried it both ways, and And making a distinction, say, when you have a short circuit operator and treating that as meaningfully different is just harder to work with, I find. So, engineering decision, I'm going to call this code on the right to 2 values, not 3 values, despite the short circuit operator. Now, you might be wondering about these empty braces, these blocks with nothing in them. Those are really there because I don't care about what's in the statement. What I'm trying to show is distinctions in execution path. So it is enough to show executes this empty statement versus does not execute the empty statement. But I can put things inside to further divide the world into different values. So if I put an if statement inside the if statement, I get a division into 3 possibilities. I have an ensemble of 3 in the code on the left here, which is different from the code on the right, which has an ensemble of 4. There are 4 distinct ways, 4 distinct paths through the code on the right. So if statements let us draw distinctions. And describing values is all about showing where you draw the distinctions. If I want to draw a great many distinctions, I could go a step further and use a switch statement. This switch statement divides the possibilities into 10 different camps, 9 for the 9 cases, and 1 for not executing any of the cases at all. I should say, not exactly 9 for 9 cases, 9 for 9 different break statements. Because again, I'm going to say meaningful difference means we executed a different collection of statements. Just an engineering decision, but I'm going to call this switch statement, I'm going to say only counts as 6 different possibilities, 5 break statements, and 1 possibility where we executed none of the break statements. So labels are not statements, and this again just makes writing code like this a little easier. So switch statement can express the idea of a whole group of distinct values. We do have other ways to control what statements are executed. A loop lets us pick one out of many different possibilities because executing more statements in a loop is distinct from executing fewer statements of loop, from executing the loop body fewer times. So this while loop has perhaps not an infinite, but at least a large number of possibilities for its execution. And if I want to show that a distinction in a large number of possibilities, I could use a loop like this. And of course, a for loop or a do loop would work the same way. The only difference is the do loop does not have it is not possible to execute the body 0 times. So that's most of what we use to draw distinctions in execution path. There is one more. And I'm going to say I was kind of reluctant to bring up the one more in this talk because it is an advanced topic. It is one of those things that you would only use in particular circumstances that honestly, I feel like if you could, you would be better off engineering your way out of those circumstances and not using this to talk about values. But it does come up. And it comes up particularly, of course, when you're dealing with an interface to something that isn't very well designed. So I'm going to bring up an example. Not an example. I'm going to bring up an object lesson. This is a function that has an interface you should not copy. This one is one that, in fact, has a Wikipedia page about humorous bugs caused by the poor design of this interface. And with that introduction, I give you our object lesson. The function is a TTY. This is a real POSIX function. You use it to determine whether a device you're talking to through a file descriptor is a terminal device or not a terminal device. And the problem comes in describing what goes on with this integer result of is a TTY, what things are repeatable and what things are not repeatable about a call to is a TTY. So let's look at what the documentation has to say about the result. The isATTY function shall return 1 if fildez is associated with a terminal. That seems very straightforward to me. I like that part of this function. What else does it have to say? Otherwise, it shall return 0 and set erno to indicate the error. You might be wondering, what if it's not a terminal? That seems to be in the otherwise. And if you read down a little further, one of the possible values for erno that are called out is e-naughty. E-naughty indicates that the fildez argument is not associated with a terminal. So how do we describe what's repeatable and what's not repeatable? What is a meaningful distinction and what is not a meaningful distinction in the result of isATTY? Well, first off, if the result is 1, it's a terminal. Like that, we can tell if the result is 1 using an if statement. The next thing that we would check would be whether or not erno is e-naughty. And if erno is e-naughty, it's not a terminal. So we have two distinct possibilities, two repeatable possibilities. That is, if we find something to be a terminal, we expect that if we call again with the same device, it will still be a terminal. If we find that something is not a terminal, if we call again with on the same device, then we expect it to not be a terminal. Both of these results we want to be repeatable. But there's an otherwise. And the otherwise is not some third distinct answer. The otherwise is there is no answer. And so, having gotten to the otherwise, we need to throw away the notion of value that we got from our earlier if statements. So, to throw it away, I will use throw, and I will say that, in my opinion, the right way to interpret the value of a failed try statement is to say that had no answer. It is a gap in our knowledge, a lack of precision, a lacuna, as the people from the humanities like to call it. So, successful try statement can show you information. A failed try statement leaves a lacuna. It's a gap, you don't know which it is. And this really complicates things because now we have the idea of compatible values and distinct values, and compatibility is not transitive. So everything gets more complicated when you are thinking about values that can have gaps in them. The same basic rule would apply, though, that distinct values, distinct output comes from distinct input. That is, I will never have a device that is sometimes a terminal and sometimes not a terminal. But I can have devices that are sometimes a terminal and sometimes don't know. And I can have devices that are sometimes don't know and are sometimes not a terminal. I just never have any device that can bridge the incompatible outputs. So that was the hard advanced part. If anybody clocked out for try statements, you can come back now. That is all of the current C++ statements that draw distinctions in execution path as measured by distinct substatements get executed. And so we have this way of letting distinct execution paths reflect distinct values. We can use this as a tool to show what is distinct. So if I had, say, a function that took a byte as input, and I wanted to say that any two values of this byte are distinct as looked at by this function, I could write a piece of code like this. I could say, if any of these bits are different, it will be I will consider this distinct. There are 8 bits here. So that lets us draw a 256-way distinction. That would be cumbersome when writing my function interfaces. So it would be nice to have a way to scale this up, to abstract it, to take this piece of code and put it one place where I wouldn't have to repeat it in various function interfaces. So I'm going to invent such a thing or borrow such a thing and just stick it in some braces and give it a name. So here, I'm going to use this word discernible, not really as a return type. It's in the return type slot. But much like void, it's really a marker that this is a special sort of function that does not return a value. It is a function that is about expressing what is the same and what is different, what a meaningful distinction in value is. And here I'm going to say, introduce a statement, discern. As I say discern bitwise of B here, it says, I care about which path B will force this function through. So they're just an abstraction mechanism. But we're an object-oriented language. We like to tie our abstraction mechanisms to our types. So I'll go a step further and introduce operator discernible, much like a conversion operator, but really it's not a conversion. It's just, this is the thing you need when you need to discern something and you just know its type, or you just have the object in front of you without a specific way to discern it. So here, discern B means I will treat two B's as distinct if they went through two different paths in operator discernible. So they're bringing it into C++ syntax. We can now talk about the usual way to distinguish two values of a particular type without having both values present at the same time. Now, of course, how you discern the value of a byte would be built into the language. That's not code that you're actually going to write. But if we step back a bit, we can look at a problem that would actually come up in library code. So let's take everybody's favorite library class, vector. A vector has 4 parts, at least in a common sort of implementation. An allocator, a data pointer, the allocated capacity, and the number of elements. And if you imagine looking at this through the naive eyes of a compiler, you might think that these are the parts of the value. That the parts of the value of a vector are the allocator, the data pointer, the allocated capacity, and the number of elements. And if any of those were different, the vector would have a different value. This is not true at all. The allocator is not part of the value. You can have a different allocator but the same value. The data pointer is not part of the value. The allocated capacity is not part of the value. The only thing here that is part of the value is the number of elements. But it gets worse. There are other things that are part of the value. That is, the value of the elements themselves are part of the value of the vector. So if we want to explain what the value of a vector is to, say, a compiler, we have to do something that's going to incorporate the values of the elements. Now, we have a mechanism for that. If we write discern element, we can talk about the value of the element in accordance with the usual manner of drawing distinctions in objects of that type. And if we want to do that for all of the elements, we will need, of course, a loop. So if we write a loop like this, we can note any distinction in any of the elements. And also, just incidentally, we have noted distinctions in the number of elements. 2 vectors with different numbers of elements will have distinct values because they will execute this loop a distinct number of times. So this little loop we can think of as explaining what the value of a vector is. And all that's left is to slap the framework of operator discernible around it and say, that's what value of a vector means. Or that would be all that's left, but we are good programmers. We notice a piece of code that can be used in many circumstances, and we would like to factor that out. So we can say, we can invent a function discernible element-wise and put that code off in that function and just invoke that function for vector. So they're using code to explain what a meaningful distinction of value is. Now, stepping back, what we've looked at today is a relationship between functions and ensembles of values. Functions execute in ways that can be described by an ensemble of values. Ensembles of values can be represented as functions. And this relationship is actually in mathematics called an adjunction. This is a mathematically precise metaphor There's a monad on the function side. There's a comonad on the ensemble side. This is creating a metaphor that says that in English we could phrase as an ensemble is a function. And in this metaphor, paths correspond to values and values correspond to paths. So a value is a path through a function, is our metaphor. I should say that is not, I think, the essentialist is. I'm not trying to say that the essence of a value is path through a function, although sometimes it is hard to tell what the essential, when you're using the metaphorical is and the essentialist is. So maybe I'm wrong about that one. But metaphorically, we have a value is a path through a function. Reasoning about functions is reasoning about values. There's one more thing I would like to say, stepping even further back, which is when we choose the name for a function, when we choose the function identifier, the identifier for a function, our best practice is not to choose words that are names. The best practice that I think pretty much universally agreed upon in procedural languages is that function names, function identifiers, should be verbs. They are the words that we use for things that happen, not things that exist the way rocks exist. I haven't quite followed that in my names for ensembles in this talk. I found myself not coming up with verbs for those, but rather adverbs. Bitwise and element-wise were my two ensembles for this talk. And that does suggest something to me, that maybe we should think of a value as a way in which a function can be executed. That is, a way in which an event can take place. And so maybe, way back at the beginning, there was a moment when instead of deciding that we were going to say things like the number of fingers is 5, which on its face is a statement about something that exists in an ontologically dubious platonic world. Maybe we would have been better off if back then someone had just said the fingers were counted 5-ly, used an adverb to describe a real action that happened in the real world. And with that, thank you for listening. Are there any questions?
On the slide where you were looking at the vector and the number of elements in it, it seems like you still need to have the size in there. I'm imagining, say, a vector of monostate, where there is no discernible properties of any of the elements, where then the only state is the size of the vector.
Yes, so remember, different collections of statements getting executed are different values. By executing the discern statement 6 times, we draw a distinction, we see that that is distinct from then executing the discern statement 8 times. So simply the fact that the loop runs longer or shorter encodes a discernible distinction in value. So we get that for free.
Okay, thank you.
Hi. I have a lot of questions and comments. But one is, what are the comonad and monad that you were referring to? Can you describe those?
Okay. Not super quickly, but I will give you the outline. You should, if you think of a function as think of a function as basically a collection of possible executions, and you can draw distinctions. This I would see differently from that. It would be observably different, or it would be meaningfully different to execute. These executions are different from those executions. That forms a category. Those distinctions give you a topology. Those functions looked at with functions with collections of executions with a topology on them form a category, and you can do basically the same thing on the value side, on the ensemble side, and if you follow it through, the actual monad, the actual monad and comonad are not super interesting. Maybe they are. Maybe, and in fact, I think the comonad is trivial. Might be wrong about that, but that's the context in which it makes sense.
Hi, that was an amazing talk. I really appreciated it. I'm not a mathematician, and I feel like I could follow most of it, but there was one part where I lost you a little bit. You were describing where operator equals equals fails, and one of those aspects was the provenance of the values. And I don't think I fully caught how the discern function captures the provenance of the values.
Okay. That one is particularly tricky, and it amounts to you can't write that function in C++. It has to be provided by the implementation, and the implementation has its own idea of what distinct provenance is. In fact, provenance is really just capturing that sometimes the compiler understands that 2 pointers will compare equal, but not point to the same thing, and will do optimizations based on that. So you have to be aware of provenance in order to avoid undefined behavior in some vaguely obscure situations.
Thank you.
Yeah, thank you for the talk. What you've got here and what you've done in a lot of your other talks is sort of set up a framework for people to reason about their code. I think that's what you're doing. And one of your fundamentals here is that if you call the function with the same input, you're always going to get the same output. And if that isn't true, then you can't reason about anything. I'm wondering if this is a more fundamental reason why we gave up on the idea of having programs modify their own code back in the day. It's not just that you couldn't reason about it, it was impractical, but maybe that was fundamentally a bad idea because you can't reason about what the code's going to do under those circumstances.
So I think there is a relation. I don't think that it's actually true that you can't reason about it in those circumstances. I think that it's just everything becomes 1,000 times harder to reason about it in those circumstances. So here, for example, I didn't point out that when you are making a call through a function pointer, you have to take into account that you expect different function pointers to count as different. If I use a different function pointer, that counts as a distinct call. That is, I don't expect function pointer A and function pointer B when I use them to give me the same answers for the same input, unless A and B are alike. So that could be expanded into an idea of how to reason about self-modifying code. It just makes everything much harder.
Okay, thank you.
Oh, we have a question online.
Okay.
How do I understand the two functors of the adjunction? And what are the objects and the arrows of the category of ensembles and ditto functions?
Okay, so I will page forward a little bit. Not that that slide has that much to remember. Maybe I won't get there. It's because there are these animations. Anyway, yes, so think of, on the function side, think of if you think of the topological space of all executions of the function, and the topology is meaningful distinctions in how the function executed. And you, on the ensemble side, you think of all the possibilities in the ensemble, and the topology being meaningful distinction in value. If I take a function and bring it over to, map it over to the ensemble side, what I'm saying is I'm going to go through this, I'm going to draw the distinction that I laid out of what it means to execute I went through each control statement, and I'm going to say, well, if it executes a different sequence of statements, that would be a different that would be a different value. So this collection of executions becomes a collection of values. The function becomes an ensemble, and that's functorial. And that's the going rightward arrow, the one over the top. And then coming back, the ensemble maps to a function just by using the exemplar for the ensemble that I described in the last part of the talk. Here is how I write an operator discernible. So the ensemble maps to discernible function. And if you go round trip, what you find is you can take a function and turn it into an exemplar for all of the different ways, all of the different collections of statements that could have been executed. The round trip on the other side, if I take an ensemble, turn it into a function, and turn it back into an ensemble, that's actually the identity functor. So things going on, things are not super interesting on that side of the adjunction. I think that's an answer. Next.
Great talk, Lisa. I have a question with regard to your thoughts on the application of this to the idea of testability. In particular, people think of code coverage as like a way to say, hey, if the code is covered by unit tests in terms of like coverage percentage, then that makes it good. Mm-hmm. And then to get better is you iterate over the values in the traditional sense
of the function and get some kind of coverage of the different values, have you thought about the implications of using values in this procedural sense as a way to say whether or not a particular function is good, has good tests?
So only lightly, but I think really fundamentally that is what code coverage is getting at in its basic idea. If you say, I want to make sure that every branch is tried in both directions, then what you are saying is, I want coverage of the ensemble of values that correspond to this function. That's not quite true, because you would actually need combinations. But it is a lighter weight thing than saying, I want coverage of all possible inputs and all possible outputs. It's a way to focus the idea, you could use it as a way to focus the idea of code coverage on the function itself rather than the subfunctions that are called. And it would also focus it on the function itself rather than the expressions within the function. So you might need to have a separate layer of code coverage, which is, yes, I handled the different ways the ands and ors could have gone.
Another online question. You defined discernible values using conditional branches. However, these branches used the less than operator. How is this different than the equality operator problem? Does value discernibility ultimately depend on bitwise discernibility?
So any notion of discernibility is going to rely on discernibility for some built-in types. Pointers being a particular example that's tricky. And yes, as far as I know, no, it's not quite true. It's nearly true that pointers are the only case where you get away from bitwise discernibility. That is, floating point numbers, if two floating point numbers have the same bits, they are substitutable. That's actually a principle that's built into how we use floating point numbers. I say almost because there is, I think, a weird case when you're doing a byte-wise copy of the pointer, the bytes themselves encode the provenance somehow, which is a little mysterious. But mostly pointers are the one that is really distinct from bitwise.
How do you meaningfully distinguish between objects that are conceptually the same but representationally different? Like a rational number, where 1/2 and 2/4 are conceptually similar but don't have the same representation.
Well, I don't have the code at hand, but in much the same way that you would distinguish between two vectors that are conceptually the same but have different representation. And often this comes down to finding a canonical format, do the calculation to put something in a canonical format and then see if they are the same. And you can do the work to get into a canonical format in expressions and other functions, and then only branch on the test for whether the canonical format is the same.
Thanks for the talk. Scrambled my brain a little bit. It's a great talk. I've been working a lot with automated refactoring, and one of the main questions we have is, how can we assert that an automated refactoring preserved some properties about the code? And I wonder if you ever thought about in terms of the control flow graph and how it maps to the topology of the properties of the value that you talked about, how we could maybe compare the topologies that are generated from different control flow graphs and use some sort of like topological equivalence check to see if we can get to the same result, even if we have a different control flow graph.
Well, the quick answer is no, I haven't thought about that. I tend to think of refactoring in terms of function interfaces, which is actually a problem because we are not in the habit of writing out our function interfaces in any formal sort of way or showing that our functions meet our function interfaces in a full and formal sort of way. So I think of it as, well, if one day in the future we had a language where we did all of that, you would do the refactoring and you would say, well, this function meets the interface, and we know that no outside function is relying on any detail that is not in the interface. So we know that it will fit and the program will behave, at least as far as interface specifications go, the same. But that's a whole different approach than what you were outlining.
From online, excellent talk. I see motifs of Liskov's substitution principle and UML's object constraint language. Are those building blocks for your talk?
So not explicitly, but both of those have informed my opinions in a deep manner that I don't think I could separate out clearly. So particularly Liskov's substitution principle is something that's just been ingrained in my thinking for many, many years.
One quick question. Thanks, I really enjoyed the talk. I really liked how you defined the meaning of a value as being defined by the paths that it forces the program to take. And to me, that sounded a lot like symbolic execution, where you define values based on the symbolic path constraints that they force the program to take. But I think I didn't quite grok the connection between this path-based meaning and the discernible function that you define. So I was wondering if you could talk a little bit about the connection there.
Okay. So the discernible function is just there to give a home, an abstraction home, to a collection of paths. So it lets us refer to this same collection of paths from many different places in our code. And something I didn't show is it lets us speak of the value that we pass to one function as related to the value that we got from another function, because they can be referring to the same discernible function. That is, the interface, the epilogue of the interface of one function could say, I discern this way, and the prologue of another function could say, I discern this in the same way. So I think I'm about out of time, and I don't see anybody at the mics. So I will say, if you have more questions, find me in the hallway. Thank you all.